So let's go to chapter 11. Chapter 11, guys, talk about capacitor sizing. So I'm going to go over a few things. Basics. And I'm not going to go, this is where we are. As you guys know, let's just set our stage here. All right. So what we're going to do, guys, is somebody of them have opened already. Okay. As you guys know, there are three types of loads that you're going to be encountering. Number one is resistive load, capacitive load, and inductive load. You guys remember that one from the days of the Ryman? So I'm not going to go talk you guys directly through this one, but I'm going to remind you of a few things here. The types of the load, Z, you guys remember Z equal R plus, we used to call it JXL. I don't know if you wrote it this way, or R plus JXC. This is the impedance is a function, guys, of the resistance plus the inductive reactance or the capacitive reactance. Here's the resistance is always here. Can you guys see that? It's always in the x-axis. The inductive reactance is either up if it's XL or down if it's XC. You guys remember that from the days of Gary? And the resistance and the inductance have a 90-degree angle between them. So if anybody ever asks you guys 2 plus 2 is what? 4. That's not 4. 2 plus 2 depends upon how you add them. If you add them algebraically or if you add them vectorially. If you add 2 plus 2 vectorially, the answer is 2 square root of 2, right? As you guys know. So this is basically what with the two types of loads you're going to be encountering: resistive load, inductive load, and capacitive load. Resistive load, inductive load, and capacitive load. Any question, guys, about these type of loads? I don't want to go deep into the impedance triangle and all this good stuff, but that's basically what you're going to do. J here is that it represents the 90-degree. That's how you write it. This, if anybody ever heard of the term complex numbers, did you guys hear the word complex numbers? When you were in schools, we went into natural numbers, real numbers, and most of us stopped at normal numbers, right? Or real numbers. Real numbers, it goes from minus infinity to positive infinity, including fractions. That's the real numbers. There is another level of numbers, guys, after the real numbers that if you do engineering, they go into it. They call it the complex numbers. This is, you're looking at a complex number, basically. Well, it's not really complicated. The complex number, you start adding numbers not on the same line. The number line, remember the number line, it looks like this. That's a real numbers from negative to positive infinity. That's a real number. If you move this axis up, now you're adding things with an angle. That becomes the complex numbers. And so, without getting too much of it, these are complex numbers, guys. You add XL, XC. Not really complicated. You're just adding in vectorially. So you have to do the Pythagorean theorem and so forth. Let me just give you a quick example here. If R was 2 plus XL was J4, so this is basically 2 plus J4, and J indicates it's a right angle. Look how easy it is to find. So here's the 2, guys. 2 is right here, right? And J is up 4. So remember how you did with Lyman? And you find Z, here's my Z, and from Pythagorean theory, Z equal, I hope I'm not going to repeat it because everybody knows that one, 2 squared plus 4 squared, right? And if you do that one, 2 squared 16 plus 4 squared is 416 plus 4 is 20 square root of 20. So that will give you a square root of 20, and if you have a calculator handy, that will get you a 20, a square root of 20, that will get you 4.5 ohm. Remember, am I right that you guys done that with Gary? The impedance and the triangles, the impedance triangle, right? That's not why. This is just the prep for what we're going to be doing. So that's basically 2 is a resistance. So here's my 2 here. And in my case, it's 4 is here. And you're finding basically the triangle, the Z. The Z. Any question, guys, about the 3 types of loads? Resistive, capacitive, inductive. 90% of the time, guys, you have resistive and inductive loads. Capacitive load, you add it. There's no value for the capacitive load except correcting the inductive load. All the motors, all the transformers that you put in a building, it's an inductive load. Inductive load. So most of the time, 90% of the time, you're going to be in this situation. The triangle is down, guys. And to correct the power factor, we need to move it up. To move that leg up. How do you move the leg up? By adding more capacitance. By adding more inductive capacitance or capacitive reactance. Capacitive reactance. So R. Any question is how to add them? 2 plus 2 is not 4. 2 plus 2 vectorially is 2 square root of 2, right? So that's basically inductive reactance. Impedance is right in here. And if you guys draw the triangle down or up, it doesn't matter. And then you can find the triangle. The other thing, guys, that I don't know if you're done with Gary is Q. Remember that Q? If this is 2 and this one Z is what? 4.5. So cosine Q is actually the power factor. So if you take cosine power factor equal cosine Q, what's a cosine? Is the opposite over the hypotenuse, right? The cosine is opposite over the hypotenuse. What's the opposite? 2. What's the hypotenuse? 4.5. So if you guys, that will give you the cosine of this angle. So 2 divided by, what is it? 4.5 equal 44. That's the worst that you can ever imagine. 44%. So the power factor of this system that I gave you right here is actually 44%. Very bad, extremely bad. 44%. See how easy that is, guys? You take the opposite over the hypotenuse, which is the Z. We found the Z. The opposite is where it's known as 2. That will be the cosine of the angle, and that will be the power factor. Am I right that you guys done that, like in the first year? Because that's not even the topic, our topic. Our topic is how to correct the power factor. Okay? Any question about this? The impedance triangle?
Power factor cosine Q.
Cosine Q, which is Q is right here, Mr. Bab. And cosine, by definition, is the opposite to the Q over the adjacent to the Q. The hypotenuse. The opposite over the hypotenuse. That's what the definition of the power factor always. You guys remember the tan is the opposite over the adjacent, and we used to do is the tan when we did lighting calculation last quarter. Any question, guys, about this? You're not gonna, unless you're doing engineering, you're not gonna see the Z and all this stuff. Here's what you're gonna see, guys, and you need to know that though. The simple form of it is the power triangle. Remember the power triangle? Can I close that one, Mr. Bab? Okay. So this is my. Here's the power triangle. You guys are, I'm sure you are familiar with what you have done with Mr. Ryman. This is, and with me, this is my true power. You guys remember that one? This is my reactive power, and this is my apparent power. We've done that, guys. Can you guys see that? True power, reactive power, apparent power. This, you have to, this is the power triangle. Power triangle. You must know that one. The power triangle, guys, you must know the power triangle. No question asked. So, just a quick reminder from the days of the power triangle, the formulas. If I want to find the apparent power equals square root of true power squared plus reactive power squared. You guys remember that? That's how we found its hypotenuse. It's the Pythagorean theory. The opposite you take the hypotenuse equal the square of the two sides of the triangle, the other two sides of the triangle. Here's the TP and here's the RP, right? RP is right here because this is opposite to this too, the same line. Anybody does not know this formula, apparent power equal the square root of true power squared plus RP squared, reactive power squared, piece of cake. Another reminder, the true power is always in kW, the apparent power is always in kVA, and the reactive power is always in kVAR. Always, always. Now that's you need to know that. So if you hear me saying, guys, I have a capacitor, and the capacitor has a 50 kVA, is this the right language for a capacitor? Capacitor is reactive power. So what's the unit for the capacitor? A reactive power, kVAR. So when you hear the people talking, guys, about capacitor, they say 50 kVAR. They don't say kVA because it's reactive power. When they talk about the systems, they say 50 kVA. You know, any question, that's must know. This formula is must know. Now, the other formula that you guys must know is power factor. Power factor, do you guys remember the power factor? We always say the true power over apparent power. You guys remember that? The true power, which is the opposite here, over the adjacent, exactly like the resistor over the impedance. The same triangle. This is a power triangle. The one that I've done before, it's called the impedance triangle. The same triangle. The opposite of the true power, the cosine is what's the cosine? Why didn't you guys correct me on that one? The cosine is the cosine opposite over the or the adjacent? Adjacent. The triangle, the adjacent over the hypotenuse. Thank you. The adjacent over the hypotenuse. What's the opposite of the hypotenuse? Sine. Sorry for that. The opposite over the hypotenuse, guys, is the sine. The cosine is always the adjacent over the hypotenuse, which is the true power over the apparent power. Very clear. So for this one, guys, if you take the adjacent to, what's the adjacent? Adjacent this angle here. Here's my adjacent to this angle. Here's the hypotenuse. So if you take this one, my friends, and where am I here? You take the 796K, divide this one by 1075. If you guys do the math on that one, what do you get? Is it 0.7? Thank you. 0.74, which is in reality 74%. Bad power factor. Any question, guys, about the power factor? Any question about the power factor? Any question about the power factor? Using the power triangle, the adjacent over the hypotenuse. Adjacent over the hypotenuse. I'll go back and correct the impedance, guys, in a second when we're done with that one. The same thing for the impedance. Always the adjacent over the hypotenuse, the cosine. Any question about finding the power factor? Everything that you guys have seen is not even what we need to do. We need to correct the power factor. We need to learn how to correct the power factor. That's why all these calculations, we have done it before. We're going to correct the power factor. So I got my, everybody knows, guys, the KW, kVAR, and kVA. And let me see if I can go and correct my mistake. Where was I here? There you go. All right, let me correct this one, guys. Can you please do me a favor? We said that, so this would be the 2, we did it fine. Yeah, we did it 2. Yeah, that's the adjacent, which is a 2. I actually already, right, this should be the, this should be the 4 here. This should be the 4. The 2 is right here. We did the math right, except here's the, can you guys see that one? Please correct this one. The adjacent is the 2. That side, that's what blew me up. The adjacent is the 2, and the opposite is right here, the 4. So 2, still 2 over 4.5. So the calculation is right, but the way we are with the 2 is wrong. So this is where the 2 should be, right here. That one is actually 4. Everybody got that one? So let's write it down because I made a mistake. So the cosine is cosine of q equal adjacent over hypotenuse. And I'm not going to spell the hypotenuse, guys. Anybody want to try? The adjacent over the hypotenuse. Could you please correct that one? Right? The 2 should be right here. That's not where I put it, right here. So calculation should be the same. 2 over 4.5, but where I put it is wrong. There always a cosine of the angle. When I say the opposite over the adjacent, that's a sine. The opposite over the hypotenuse is a sine.
So the cosine of the angle is adjacent.
Hypotenuse all the time. Any question, guys, about this? Please, everybody correct that one. My mistake. Cool. Adjacent over hypotenuse. The calculation is right. The only thing is where I put the 2 is wrong. Okay. Mr. Brad, did you do that? Okay. All right. So that's basically the whole. This is you guys who have done that before. I know you have done it with me. Now the idea, guys, is correcting leading power factor and lagging power factor. When we have a leading power factor, you always guys go if the current and the voltage. If the current leads the voltage, that's a leading power factor. If the current lags the voltage, it's a lagging power factor. Who cares? If you have a leading power factor, you have a lot of capacitance. If you have a lagging power factor, you have a lot of inductance. What's best? Is it good to be leading or lagging? Both of them are bad. What's the best for any electrical system? To be 100% power factor means no leading, no lagging. And just to give you a quick idea of leading, lagging. So if this is my voltage, guys, if this is my voltage coming over here, and I need my current to start at the same point and end at the same point, different magnitude. This is my I, this is my V. This is my V. This one is 100% power factor. That's how it looks like, 100% power factor. 100% power factor. And you can see that the voltage and the current, they stop at the same time. Let me show you a leading power factor. A leading power factor, let's say I'm going to use a green here just for the. So here's my, come over here. This is my I. And look at the voltage stays the same. Can you guys see the voltage stays the same? This one is leading power factor. The current leads the voltage. Always by the voltage. Always go by the voltage. Can you guys see that the current starts before the voltage? The current starts before the voltage. Let's see a lagging power factor. The opposite. The lagging power factor is something like this. So this is also an I current, lagging power factor. Lagging power factor, which starts, the current starts, lags the voltage. That's the word, lag, leading. Always start, guys, with the current, always reference to the voltage, because the voltage is what we reference to. The current lags the voltage. The current lags the voltage. Here, the current leads the voltage. That's where you're leading lagging power factor. 90% Brad of the time, 99% of the time, you are in a lagging power factor. Why? Lagging power factor, guys, comes from inductive reactance. Inductive reactance, we have all the motors, all the transformers. Everything that has a coil will create a lagging power factor. Everything that has a coil create a lagging power factor. So 90% of the time, you're going to be in a lagging power factor. Lagging power factor. Any question, guys, about this? Leading, lagging power factor? Now we know what leading, lagging. We know what the kVAR, kW, and kVA. Now, how do you correct a bad power factor? That's what this chapter is all about, guys. How do you correct a bad power factor? 99.9% of the time, you are lagging power factor lower than 100. 99% of the time, and you need to correct it as close to 100 as you can. So that's 90% of the time. Okay, there are two ways, guys, of correcting power factors. Let's start with I'll get into that one. There are two ways of correcting power factors, guys. The most common way of correcting power factor is adding capacitors. Adding capacitor. Just to give you an idea how do we correct power factor with capacitors, I'm going to give you a very quick example. Very quick one. Look at this. Let's say I want to correct the power factor. I'll give you an example. Example number 1. I have a system, and the system, power system. The power system, guys, have a KVA equal 900 kVA. That's the true power. That's the the apparent power. The true power equal 500 kVA. The true power the true power equal 500 kVA. Okay, and thank you. The kW. I'm thinking of another kW always. And so let's draw the power triangle here. So here's my my apparent power. Can you guys see that one? This is the 900 kVA. Where's the other one? This one is the 500 kW, and I need to find the reactive power. Can you guys find the reactive power from this triangle? I need to find the reactive power. Reactive power equal what? I have the apparent power, the true power. I need to find the reactive power. You guys know how to flip reactive power equal square root of apparent power squared minus true power squared. Everybody knows how to do that, guys? The formula, apparent power squared minus the true power squared. We're flipping a Pythagorean theory. And if you guys do this one, you're going to find 900 squared minus 500 squared, piece of cake. If you guys do the 900 inverse squared plus not minus 500 inverse squared equal, take the square root of it. I came up with 748. Anybody came up with something different? 748. K what? Brad, one more time. Correct me now. We're doing the reactive power. K var. Thank you. Var. K var. Did I do it right? Anybody came up with something different? Any question, guys, about finding? If I give you 2 out of these 3, Spencer, you should be able to find the fourth one. 2 out of 3, you should be able to find the third one. So the reactive power, we've just found it, guys, as 748 var. Now that's not enough. That's finding number, let's say A, the reactive power. A, find the reactive power. B, I'm going to do B here, guys. Find power factor. Find the power factor. Anybody can tell me what the power factor is, and what do you do it? Power factor equal, what the power factor equal? The true power over the apparent power, which is 500 K over 900 K. So if you take 500, it's basically 5 over 9, equal 55, 56, 56%. Everybody can see that one, guys? 56% equal 56%. What is that percent is not coming? 56%. 56%. Always equal, the power factor equal the true power, which is the adjacent over, this is my Q, over, over the hypotenuse. Any question, guys, about the true power? Now let's correct the power factor. Let's go ahead and correct the power factor. Let's go ahead and correct the power factor for this baby. Let's go ahead and correct the power factor. Any question, guys? I have a system of 900 kVA, true power 500 kW. Now, Mr. Bew, where the heck would you get these numbers? A building like Dunwoody, how would you know? This number, Mr. Bew, it's easy because you can measure the current and the voltage, multiply the current by the voltage by 1.73, you got this number. The apparent power guy is very easy. Measure the current. Mr. Bev, every one of us knows how to clamp on ammeter, measure the current. Easy. Measure it, measure the voltage. We measure it, multiply the current by the voltage. And because it's 1.25, because of it's a three-phase, you multiply by 1.73. Multiply by 1.73, you get the 900. How do you get the 50 kW though? The 50 kW, guys, you need a kilowatt meter. You get your kilowatt meter, you can measure kilowatt, the true power, you can measure it. You can't calculate the true power if you don't have the power factor. You have to measure it. So this is measured, this is calculated after you measure it. If I divide them by each other, this is what you get. 56. Now, Mr. Abab, if I tell you, I want you, being the engineer, to go correct this power factor to 100%. How much kVAR capacitor you need to add to correct this to 100%? Anybody can tell me? How much kVAR you need to correct this one to 100%? To correct this one to 100%, guys, you have to eliminate this amount. How do you eliminate this amount? 748K. By adding, this is inductive reactance, shooting up. If I add the same amount shooting down, what's happened to them? They neutralize each other. They cancel each other. So just by looking at this, if I tell you, how do you correct this system into 100% power factor, you see, Chad, no problem. I can add the same amount, 748K K var. This should be a var here. Yeah, K var, 748 K var, except capacitance this time. So I can buy myself a capacitor that can give me 748 K var. Done. And that should eliminate it. Let me tell you how that would work, my friends. So to correct, here's my capacitor. I'm going to add this one. This is 748 kVAR capacitance. Capacitance that I added. So when you guys add these two together, there's the inductance moving up, the capacitance moving down the same height. So as now the triangle, as if these don't exist. They neutralize each other. One is going this way and the other one going the other way. They basically add each other to zero. Right? Look at this, is pointing 748 pointing down, 748 pointing up. So when they add each other's up, guys, they add each other's up to zero. So the triangle will look something very similar to this. Will look, this is your triangle. This is one line. So in a case like this, here we go. In a case like this, okay, there you go. We have this one. So in a case like this, your triangle, after you get corrected, it's going to look something like this. So I have 748 kVAR, and I have another 748 kVAR. And what do you guys think these, when you add them up, you take 748 minus 748 K and K, they add each other up to 0 kVAR. Right? Because one is going up, one is going down. So then the triangle is actually nothing other than just this. This is your triangle now, with just one line. So the apparent power equal, and the true power, what was the true power, Brad? 500? 500 kW. Now, can you guys see it's as if this triangle kept going down, down, down until the apparent power equal kVA. The apparent power and the true power are equal. Can you guys see that? The triangle kept going down, down, down until they match. That's ideal situation. Then let's find the power factor. Power factor equal true power over apparent power equal 500K over 500K. I don't know about you guys, but this is 100%. That's correcting to 100% power factor by making by adding the same amount of kVAR to the system, the same amount of kVAR, capacitive kVAR to the system, equivalent to the kVAR that the system has. Any question guys about this? Any question about this? Now, how do you correct power factor? There are two ways of correcting power factor, guys. The most common way is you add a big bank of capacitors. When we went to Boston Scientific, did you guys see when they pointed the capacitors at the top of the MCC? Big bank of capacitors. We all know what a capacitor is, right? Big bank of capacitor bank right at the top of the equipment. That's number one. Number two, the one that you guys are not familiar with is synchronous motors. They have synchronous motors, and believe it or not, they have a rotating motor, unloaded motor. Spencer, you have a big fat motor sitting there. There's nothing. The rotor is sitting here, and there's nothing attached to the rotor. No fan, no pump, nothing. So it's just sitting there, unloaded and spinning. A synchronous motor. And if you guys remember, the induction motor has no wires coming out of the rotor, right? But the synchronous motor, what they do is they have a DC. They bring a DC. There is a coil inside the rotor, that rotating part. And they bring DC voltage to excite. They call it exciting the synchronous motor. Long story short, by adding more DC, they over-excite these motors. And these motors, instead of now consuming kVAR as they should, when they over-excite them, they start giving kVAR the opposite direction. Normally, the motor is supposed to consume the kVAR. So the kVAR is coming from Excel into your motor. When they over-excite the synchronous motor and don't load them, they're not loaded, they do the opposite. They flip it and start pumping kVAR. It's acting like a capacitor. So by adding a synchronous motor in your building, like the industrial building that we have, they add condensers, a big synchronous motor, basically 1 or 2, and you can size it in kVARs. You solve the problem of your low power factor. The most common ones that I'm familiar with is capacitors, but you can also size. And where would you use the synchronous motor, guys? In bigger plants, we have tons and tons of motors running. You can run another motor unloaded, and that will be synchronous motor. You over-excite it, adjust the excitement to give you a certain amount of kVAR to solve the problem of the power factor. Any question, guys, about the power factor? Two ways: capacitors or synchronous motors. You over-excited. And either way, you need to give you, can you guys see the 748? You need to push, you need to give kVAR instead of taking kVAR. How do you give kVAR? By making it pointing down instead of pointing up. To cancel the existing kVAR. Any question, guys, about this? Let me show you the example that you have in your book. Okay, here's an induction motor, synchronous motor. Can you guys see that this synchronous motor, like any other motors, you size your horsepower, blah, blah, blah. The only thing, Brad, that's different out of this motor, there are wires coming out of the rotor. Induction motors don't have wires coming out of the rotor. Can you guys see that? These wires? These are wires coming out of the rotor. That's the single most important thing about synchronous motors. And then you have a control circuit. This is the most important thing for synchronous motor. So you have a control circuit here where you can bring DC, you can adjust all these things and put 24, 25, 60, 70 DC volt in the rotor, guys. And by adjusting, believe it or not, by adjusting the synchronous motors, the excitation for synchronous motor, this synchronous motor start pumping, giving kVAR. How much kVAR? Depending upon the size of the motor and the excitation. Size of the motor, the excitation. So most of the time, guys, the motor will be consuming the kVAR. kVAR is going this way. When you over-excite this motor, this kVAR is gonna be this way. kVAR. So it's pumping kVAR into the system. That's all what we care about. Pumping kVAR out of the motor instead of taking kVAR. If you're pumping kVAR, you're basically canceling the kVAR that's in the whole building. So without getting into the control system, there's a control system that can adjust how much kVAR based on the horsepower and based on the excitation and so forth. As far as you guys are concerned, you're going to size these, and I'll show you how to size them in kVAR. I want this amount of kVAR, then there will be a chart that this amount of kVAR equivalent to 50 horsepower synchronous motor. Bam, then I need a 50 horsepower synchronous motor. Most of what I've done is really capacitance, so you don't have to worry about the horsepower of the synchronous motor. Just 50 kVAR capacitor, done deal. 50 kVAR capacitor, done deal. Any question guys about this? I want to let you guys know that rotor. Can you guys see the rotor right here? There is nothing tied to this rotor. Nothing. No fan. No pumps. Nothing. It's just a. If you go to our labs, when you guys went to our labs, did you see that rotor when you energized with Gary? The rotor was just rotating. Nothing. No fan attached to it. No pumps. No saw. So these are unloaded synchronous motor. Unloaded, no load on them. Synchronous. The only difference between them and the induction motor is they have a wire coming out of the rotor. Can you just see that? These two wires, the field wires. That's all. Why do they do them? Because by pumping, by pumping voltage in the rotor, they can make this motor run at 800 RPM. This will be an 800 RPM motor. If it was an induction motor, Brad, you cannot get an induction motor to run at 800 RPM. You can get close, but you can't get 800 RPM. You can get 750, 780, but you can't get 800. Because to get the 800, the rotor has to run at the same speed of the synchronous speed. Remember the slip and the synchronous speed? The only way you can make the rotor lock speed-wise with the synchronous speed is by adding a DC right inside the rotor. We have slips and they put a DC and the rotor is rotating and attached to a slip that's bringing DC to it. They lock them in synchronous. When we went to Cummins, guys, did you hear what every machine that they were talking about saying what? Synchronous generators. That's how they do the synchronous generators. And they were talking about 1800 RPM. Almost all motors, generators are 1800 RPM. The same concept, synchronous generators. And I don't know if you remember how they were saying, guys, you can excite by putting DC excitation, control the frequency by excitation, and pick the load by adding more fuel, right? I don't know if you remember when Tim was talking about to maintain the frequency, we add more DC voltage on the rotor, and to pick up the load, we basically burn more fuel. Anyway, so if you get that one, you add more DC, you're pumping power out. Except the synchronous generators, they're pumping what? They're pumping power. These guys are not pumping power, kVAR. They're just doing the same thing, except you can't use this kVAR to run a motor. You can use it to kill the bad news of a motor, which is the inductive reactance. Any question, guys, about this? Synchronous motor, unloaded, overexcited, solve the problem of your bad power factor. Okay, I'm going to give you guys a quick break here after this one though. Let me show you. They call them condensers or synchronous motors. Look at this. I want you guys to look at this. These are 520 kVAR. These two are parallel and they're pushing this way 520 kVAR. Look what they're doing. They're pushing it this way. Now, I want to bring to your attention, guys, the system here. Here's my kVA, kW, and lagging 720. Up to this point, I want you guys to pay attention to this block here. And also to this block here. Can you guys see that? And this block. That's the only thing I want you to pay attention to. These three blocks. So at this point, guys, this power is coming in here. And also these two blocks are coming in here. So I have 520 and I have 720. 720 minus 520. What do you guys get? We get 200. 200 kVAR. That's it. So my kVAR of the system is 720 kVAR at this point. Up to this point, when I tied the synchronous motor to the system right at the switch gear, look what they did. They killed it. They killed how many? They killed close to 500 out of it. 500, and the leftover was what? I lowered it all the way to 200 kVAR. Well, how do they kill it? Neutralize it, whatever name you want to use it. Neutralize the effect of it. Because one is pushing it this way and the other one is pushing it the other way, so they're counter-affecting it. Now, I want somebody to tell me, if I want a 100 power factor, how much kVAR do I need these guys to pump in? 725, 100 power factor. This should be, to make it 0, 720. So if you want this to be 100 power factor correction, guys, see the 720 kVAR coming in the system. I need to go have a synchronous machines that pump 720. So it becomes 720 minus 720 equals 0. That's a power, 100% power factor. 100% power factor. Any question, guys, about this? That's what the synchronous machines do. I'm going to show you guys how the power factor. Let's take before. This is the before right here. This is before. This is really good example. Let's look at the power factor before. This is piece of cake, Chad. Power factor equal. What's the true power? 796, right? 786 or 96? 96 over. What's the apparent power? The apparent power. 1076. 1076. Is that true? Am I reading it right? Yep. 796, 1075. This one is 75. Okay. So if you guys 1075. If you do that one, the power factor. If you guys do that, you're gonna find 796 divided by 1075 equal 74, right? The power factor here is 74%. That's before we correct. This is the before. True power, apparent power, true power, reactive power, before correction. Let's look at after correction. I want you guys to look at the after we corrected. This is after what? After we correction. How do you know it's after? Because now I tied the induction motors to it, or capacitance the same way. Look at the power factor, guys. Power factor equal. Power factor equals 796 stays the same. 796, no change in it. Divided by 820. 821 K and K. So 796 divided by 821 equal 97. 97% power factor. Beautiful. 97% power factor. Beautiful. Can you guys see the before and then after? What happened to the power factor? I want to bring to your attention, if you want, this is one of the most important things if you guys want to understand power factor correction. And if you want to listen to your friend Chad, always look at the true power. Anything happened to the true power, guys? Is there anything happened to the true power? No, true power stays always the same. Before and after the correction, true power always stays the same. So the true power stays the same. The only thing that changed, the reactive power. Reactive power goes down, and in return, because the reactive power went down, the apparent power went down. So look at the apparent power right now, it went down. So who cares? Now this 100 amp that you're coming from Excel Energy, you're actually using 95% of it instead of before. You're only paying for 74 of this 100 amp. You used to be you're taking 100 amp and you're paying 74 amps for 74 amps, and the rest is just sitting there screwing up in your system. Now when you correct it, you're taking 100 amp out of Excel Energy and you're paying for 97% of it. Good. Who cares, Excel guys? If you have a power factor like this, they penalize you because they're giving you a lot of amps and you're not paying for most of it or for some of it. Any question, guys? This is this because when it comes to Excel, guys, Excel care about this value here. This is the value that Excel would care about right here. They want this one to be with the power factor as high as you can because that's how they size their transformers, their transmission lines is sized based on the apparent power. That's exactly what the current is going to go in the wire. And then if your power factor is screwed up, then you're paying. Look at this. You're taking this amount and you're paying for this. Here you're taking less amount from Excel, but you're still paying for the same amount. You mean? So 97% power factor. Now Spencer, this showing synchronous condensers, aka synchronous motors. If these were Banco capacitors, it would be exactly the same. Banco capacitors, guys, it will be completely exactly the same. Just that thing here, instead of two condensing units, it will be a capacitor tied to the system. Capacitor tied to the system. Any question, guys? Any question? Any question? This is one of the most important things to understand power factor correction is. Before you correct, the power factor is screwed up. After you correct, the power factor is okay. For example, if you guys corrected the switch gear, right at the switch gear, then from the switch gear up to Excel Energy, we're corrected. Below, from the switch gear down to the panel here, your power factor is screwed up right here. If I put my capacitor guys down in the basement in the switch gear, the power factor continues to be screwed up in this panel. But it's good where? It's good from the switch gear down and up. So the power, I want you to look at right here. If I have any loads right here, the power factor is still screwed up. It's corrected from here up, which is where Excel Energy is going to interface with you, or the power company. Any question, guys, about the power factor correction? Should we take a quick break and I'll take example? Thank you. If I can, guys, have you back. Thank you.
Are you recording?
Yeah, I'm recording. You guys are looking at a condenser. This is a picture from the project that we have. The condensers are sitting right in here, tied to the control system, and from here into the busway system feeder. If you guys remember when we looked at the busway feeder and we showed the feeder going all around the manufacturing floor, this is just a way of connecting the condensing unit to the busway to correct the power factor for this manufacturing floor. Nothing really gimmicks to it. There was some control and disconnect and so forth. The one that I'm going to spend, if you have three-phase load, guys, in order to, for motors, I'm going to show you how two ways of correcting power factor. But for motors, guys, to correct the power factor for a motor, you need to know the amps. You need to know the amps, right? I need to know the amps. I need to know the voltage. And if you take apparent power, if you guys remember, the apparent power equals 1.73 times I times V, right? That's my apparent power. And the true power for a motor, everybody knows what is the true power for a motor. The true power for a motor, including the efficiency, is the horsepower times 746, right? Times 746. The true power times 746. So that's basically your true power. So you take the true power divided by the apparent power, you get the power factor of the system. There's some efficiency going in here, guys. There's the efficiency that's going on. Okay, true power efficiency. Let me just true power out over true power n divided by. Don't forget that divided by the efficiency. There you go. So that's how you find the true power of a system for a motor. You take the horsepower of a motor multiplying by 746 divided by the efficiency, that would be the true power n of the motor. And then to find the power factor of a motor, guys, power factor of a motor, piece of cake, Chad, true power over apparent power. Done. So one more time, guys. You go to a motor, you measure the current, easy, piece of cake, grab the ammeter, read it. Now, Brooks, what happened if you measure phase A, phase B, and phase C, and you find phase A 90, phase B 91, phase C 95? What would you do, guys?
Mean.
Thank you. The mean, average them. If you guys find the amps different, you're gonna average them. The same thing for the voltage. If you go phase A to phase A, phase B to phase C to phase A, and they're different values, what do you need to do? Average them. If they're different values, average them. Because ultimately, I need one value to multiply here. Average them. That's how we do it. And then horsepower, we know what the horsepower is. Times 746 divided by the efficiency. Efficiency is on the motor, the nameplate on the motor. And that will give me the true power. That's how you find the power factor of a motor. The power factor of a motor. Power factor of a motor. Any question, guys, about this? Any question about this? I'm not going to ask you to find a power factor for a motor. I'm going to ask you how to correct the power factor for a motor in a second here. That's why I need to go. Now, Chanel decided to answer, look at his stuff right now. So I deleted it. Okay, so here's there are two ways of correcting for power factor. Two ways of correcting for power factor. and I want you guys to tell you the best way is to correct right at the load. What we have done in the past, guys, if you want an idea, if the this is not it, horsepower of equal or more to 15 horsepower, correction needed. Rule of thumb, Brad, if you have a motor 15 horsepower or larger, correction is needed. Rule of thumb. If you have less than 15 horsepower, 5 horsepower, 10 horsepower, 7.5, we can live with this. Does that make sense, guys? So if we have a horsepower, if the horsepower is 15 horsepower, correction is needed. Now, 30 horsepower, needed. Any question, guys, about kind of rule of thumb, cutoff, 15 or larger, needed, less than 15, optional? And all these are optional, by the way, except the utility comes back to you and penalize you. Okay, so we understand where do we need a horsepower correction, 50 or larger. Now, Camille, my friend, you have two ways of correction. You can either correct right at the motor. Can you guys see that? That's what you have seen when you guys went to Boston Scientific. You saw these capacitors sitting right at the top of the MCC. Can you guys see where they tie it? Look where they exactly tie. This is the best way of correction, right here. The best way of correction. Then you can size the overload and size the starter and size the fuse based on the corrected amp. Let me just give you a very quick example. If the amps that the motor was taking, apparent amps, if the apparent amps here was 100 amp, after you correct, guys, right here, it might go down to 90 amps. The apparent amps. If the apparent amps that the motor is taking 100 amps, after you correct, this is the demarcation point right here. After this point, it becomes 90. Now, I'm just giving this example, 90 amps. So you correct, you size the overload based on 90 amps, the starter based on 90 amps, and the fuse based on 90 amps. Okay, so that's the best way of doing it. The second way of doing it, another thing, Brad, can you guys see with me that every time I start this motor, what happened to the capacitor? The capacitor is energized with it. So the capacitor will de-energize every time you de-energize the motor, which is good. You guys know why this is good? Because you don't end up with leading power factor. If you don't turn, you know what happens if you don't turn the capacitors off and your load goes down, like you shut down for whatever reason, the air handling unit went down, right? We shut it down. We don't need more here. But the capacitor stays on. You know what happened? You end up with a leading power factor higher than 100. You know what a higher than 100 leading power factor? They call it leading power factor. Means if you go to that receptacle here, you're supposed to get 120 volt. Now you're getting 150. High voltage. What's the problem with high voltage? Burn equipment. Equipments don't like high voltage or low voltage. They like the exact voltage. So a higher, if the power factor is leading or lagging, it's bad news. We want it to be, most of the time, you want it to be between, the best power factor is between 94 and 100 lagging. You don't want to go leading. And if you have capacity, if you have motors, guys, you're going to hear, if you have generators, if you have generators and have a leading power factor, you have a lot of problems with synchronizing, like we said. It creates a lot of problems with synchronizing too with leading power factor. Most of the time, 99% of the time, you're going to be lagging, and you're going to be between 94, the best is 94 to 97 even, not even hit the 100, because if you hit the 100 and one load goes down, you move into the leading. So between 94 to 97 is the best correction. Okay, but this is the best way, guys, because every time this motor is energized, the capacitor comes on and neutralize the effect of the inductive reactance coming out of this 50 horsepower motor. Suppose that this one is a 50 horsepower motor. Every time that comes on, now this is on at the same time. We corrected this problem. So as far as the system concerned, as far as the rest of the system concerned, right? This is connected to a system. As far as the rest of the system concerned, this baby is not an offender. It's not an offender. Because every time it comes, it corrects itself. Every time you turn it on, it corrects itself, right? That's perfect. And when you turn it off, when you turn it off, it will turn the correction off. Why? Because if you keep the capacitor on, now you have an issue. You could have an issue of leading power factor, high voltage for other equipments in the system. Best correction is capacitor, the motor goes on with its own capacitor, goes off with its own capacitor. So you don't have a leading power factor issue. Any questions about this? See how that contactor, the starter, is controlling both these equipments. So that's the best way to do it. The second way to do it, guys, is look at this now. Can you guys see that one? That's another way of doing it, where you have, can anybody tell me what the problem is? If I have 100 amp here, up to here, it's 100, it's still 100 amp. Up to this point, it's still 100 amp. And right in here, this is the demarcation point. It turns into a 90 amp. And I'm just showing these numbers. The correction happened right at this point. Why? Because this pumps 10 amps in the opposite direction. This pumps 10 amps in the opposite direction, reactive 10 amps, and kills this 100 into a 10 amps. So the correction happened right from here up. Okay? That's fine with me, right? So I corrected every time this 100 amp motor comes in, I corrected the power factor for it. What's the issue with this though? If this is on, this will be on. What if I turn this off? What's going to happen to the capacitor? Still on. The capacitor is still on. So this could get you guys in a situation. You might get you in a situation where you have over voltage, over correction. So how do you solve this problem, DJ? You come over here and you put a contactor, starter. Right? So a starter, I put a starter and I interface. See these two starters? You have a control circuit that when you push the button and you start this motor, guess what? At the same time, you turn this capacitor on with the starter. And when you turn this motor off, at the same time, you turn the capacitor off. That's one way of controlling when the capacitor is going to come. Guys, if you put the capacitor on and leave it on and the load is off that you need to correct, you end up with a leading power factor, high voltage, bad news. Just remember, you don't want to solve a problem to create another. Any questions about this? What you guys going to be doing with Chad is we're going to be sizing the conductors, the overcome protection device, the disconnect, and the capacitor in a few seconds here. We're going to be sizing the capacitor. Can you guys see that? The capacitor number 1. We're going to size the conductor number 2, number 3, and number 4. These are what we're going to be sizing. Find the capacitor, find the fuse, and the disconnect, and the conductor for this system. Any question, guys? Any question, my friends? So this is called local correction. Local correction, guys, you correct right at the load. Right at the load. That's local correction. Wherever the load is, you correct right at the load. The other one, guys, is I call it global correction. Instead of correcting right at every load, you come all the way, Spencer, to the switchgear. I have my 4,000 amp switchgear. I measure the power factor of the switchgear and screw it up, and I correct right at the switchgear. One big bank of capacitor right to the switchgear. So there are two types of correction. One more time, guys. One is local. You can see it. These two are local correction, or one is a global, right at the switchgear. Right at the switchgear.
Is there a better way?
This is the better way. This is better way. Cost effective is different. This is more expensive, better way. Correcting at the switchgear is less expensive, but you're taking a chance. You know what the taking a chance? You're taking a chance of over voltage and overcorrecting and leading power factor because you're not turning them off. Guys, just to give you an idea, the utilities have, I don't know if you've seen on these transmission lines, they have capacitor banks. They go on and off. These capacitor banks the utility have, every time they're looking at the voltage, they have monitoring system. They're smart. They look at the voltage. Every time the voltage on the transmission line dips below, say, 10%, it has a sensor that sends the signal to the contactor, shut the contactor, close, and bring the capacitor up. So raise the voltage. And when the voltage goes higher than a certain value, because the load is went down, it opens up. So it's dynamic, it's electronically controlled capacitors. I don't think they do them in building. I've never seen them in building. In buildings, you turn them on and turn them off, but you don't monitor the voltage. In utilities, they monitor the voltage all the time on the transmission line. If the voltage goes up, turn them on. It goes down, turn them on. The voltage goes too high up, turn them down or turn them off. You know, and there are multiple steps. They can turn half of them, 2/3 of them, so it gives you the exact, close to the exact value that you want. Any question, guys, about this? So Camille, you're going to do you're going to do, guys, in a second, one thing with Chad. You're going to size these 4 things for a capacitor. That's what we require to find. Find the size of a capacitor. And Brooke, since we're designers, we always talk about wires and disconnect and the fuse, right? Like a motor. Remember how we did with a motor, guys? We always find the conductor that feeds it, the overcome protection device for it, and the disconnect for it. And in this case, we need to find the actual size of the capacitor. Any question, guys, about this? Any question about this? So if you move in here, capacitor, this is testing a capacitor, guys, for open and close, basically. And you guys are not going to be testing capacitors. So I'll go directly into correction. Let me tell you, correcting power factor. Correcting power factor. 2 ways. Number 1, local. And number 2, main. I'm going to call it main, local correction, and main correction. Well, I'm going to show you an example where if you guys, here's a switch gear. Look at this. Switchboard coming here, a switch all the way, and from here going all the way here to a motor. Okay? So this is a switch gear. Panel -1, panel -2, panel -3. Just to give you an idea, guys, what the local is, the local would be right in here, and you put your capacitor. So this will be number 1. Can you guys see that? This is a local. Global or main, you come over here, guys, right at this, and you put your capacitor right at this point. This is my capacitor. This will be number 2. Can you guys see that difference? Way at the switch gear or down at the level of the motor. And remember that we said 15 horsepower or higher. This is kind of a rule of thumb, 15 horsepower or higher. Any question, guys, about which one of these is the best? Local is the best. This is correction main, best and more expensive. This is cheaper. That's basically, the main is cheaper. You just have one there. Why expensive? Because if you have another motor, what do you need to do? You need to correct for the second motor and the third motor and the fourth motor. Versus here, I'm not showing another motor. So suppose there is another motor over here, right? Here's my 30 horsepower motor. Well, guess what, Spencer, my friend? You need to come from here. There's my capacitor. See how many correction you end up here? Which is fine. For every motor, you correct it right there. The second one is you only have one big bank at the main. You go measure your worst scenario, guys, when the power factor is really bad, and you set your bank of capacitors, and you might have to put some monitoring system on it, or size it slightly. What they do, if you were to do this one, make sure you size no more than 90. Size up to 90% power factor, because if some of these loads are turned off, then no matter how high the power factor goes, you still have between 90 and 100, that range to go up before you start going leading in the other direction. Any question, guys, about local correction between and main? A lot of people are forced to do the main. Main forces by utility. The utility care about here. That's where they care. If your power factor is low here, we're going to go penalize you. They measure it right at the main here. Okay? Any question, guys, about local and main correction? And by the way, I'm showing capacitors. Spencer, it could be also in condensers or synchronous motors. Same way. You put them here, or you put them right at the top. Any question, guys, before I give you one example calculation? Most of the time, Excel, guys, you need to correction must if power factor is less than 90%. Almost always, guys, utilities, they look at the 90 cutoff. If your power factor is 90 more, and they have a lot of calculation that they do, but if it's 90 or more, you're good. If it's less than 90, you have to start thinking of power factor. And Spencer, where do they look? They don't care here. Utilities don't care at the bottom, guys. They look right at this point, right at this point. They want the power factor to be 90% or more. They need the power factor right at the switch gear, right at the main switch gear, 90% or more, 90% or more. They allow you guys, without getting into too much details, they allow you, when you start the chiller, to go down a little bit, start major motors. But on average, when you're running fully and everything is right, they want for a certain amount of time, they want your power factor to be maintained 90 and higher. 90 and higher, not less than 90. Any question, guys? And look where they measure it. The utilities care about this. You care about inside your building. That's you, right? If I want to correct locally here, that's me. I want to correct for my own consumption, because what's the value of correcting locally here, Brad? Because the current goes down, then the voltage drop losses is down. Great idea, because you corrected the current, less voltage drop, less losses in the conductor. So there's a lot of advantages of correcting locally here for the customers. Obviously, you're not forced to correct locally here, but you're forced to correct right at the main, at least, by the utilities, if you have a commercial or industrial customer. Any question, guys, about the power factor correction? Okay, let's take an example and go correct for a system. I'm going to show you this example, guys, and I'm going to go directly before and correct for this system. Mr. Irbab, I have the following example number one. Example number one, I do have a power system, and I care less about all these motors and all this good stuff. And I need, here's my switch gear. This is my switch gear, and I need to correct, add a power factor here, fused with a capacitor capacitor bank. I need to correct the power factor for this system. Here's what we know about this system. We know about this system, my friend. Power factor, the power factor of this system is 80%. Bad news, 80%. The current of this system is 1,000 amp. The voltage of this system is 480 common, 480 volt. Okay. Okay, 1,000 amps, 480. Okay, so that's basically what I know about this system. And I need to correct, yeah, and then I need to correct to a power factor. I need to correct to 97% power factor. The utility told you to correct to a 90% power factor. And use the mean. We're using the mean. We care about the mean here, or mean. Okay? Any question, guys, about this? Everybody knows what we have. We have a 1,000 amp, 480, 80% power factor system. And I need to add a capacitor like I'm showing right here. A capacitor. And I need to find the following for the capacitor. I need, number one, guys. This is number one. Oops, let's use a green. Number one. The first thing I need to find is the capacitor size. Number two is the conductor size for that capacitor. Number three is the overcome protection device, and number four is the disconnect. I need to size the capacitor for this system and then size the disconnect, the overcome protection device, and the cable for this capacitor. Very typical. This is the existing. This one is existing situation. All this is existing. And the rest is correction, 97% power factor correction. Oh, there are fuse. Yeah, 3 is a fuse. 4 is a disconnect. Any question, guys? Very easy. You're going to find it very. Any question about this before I go find these 4 things? They move? A little bit. Okay. So 1, 2, 3, the capacitors. All right. So the first thing, number one is cap size. The first thing I need to do is a cap size. To find the cap size, guys, step number 1 to find the cap size is to do the following. You need to find the true power. The true power always equals 1.73 times voltage times current times power factor existing power factor always. Okay, let's go do that, right? So 1.73 times what's the voltage? 480 times what's the current? 100. 1,000 times what's the power factor existing? 0.8. And if you guys did all this, existing power factor, I have 664 kW. 664 kW. No, don't take us out. Any question, guys, about this? Is the calculation math right? Everybody? Math is right? Okay. That's step 1. Step 2. Step number 2. Here's what you need to do. Take power factor. What was the power factor? 80% power factor and 90% power factor. Take them to, I want you guys to go to page 64, electrical, wiring, industrial, page 164, and that will be Fig 11, table 11-1. Okay, are you guys there? We're going to go find the multiplier. You find a multiplier. If you guys look at, this is the table I'm looking at. The power factor at the top are the corrected, the one that I need to correct to. Can you guys see that? The power factor on the side are the original one. On the side here, original one. On the top, the columns are the corrected one. So can you find the multiplier from this table, the multiplier for an 80% and 90? 80 original, 90 correction. So don't forget that. That's 80 as original. This is corrected. Corrected. Okay. What's the multiplier, guys, for 90? Is it 90 or I'm going to correct to what's the? 97. I'm sorry, 97. I'm going to correct to 97. 97. What's the 97 and 80, guys? What's the multiplier of 97 and 80? Everybody came up with 0.499. Can you see it? 97. One more time. Right here. Here's the 97. Go all the way down. Here's the 80 across, and your multiplier is 0.499. 0.499. Okay. So then from here, My M multiplier is 0.499. You're going to see why I found this number. Any question guys about this number? 0.499. Any question about this number? So step number one, find the true power. Step number two, find the multiplier. Piece of cake. The multiplier is easy based on the columns. The columns are corrected. The rows are original. And okay, everybody knows how to read this, guys? This is the original here, corrected on the columns. All right, so piece of cake. Let's go to step number three. Step number three. I'm sorry?
You just work on the multiplier or something?
Yeah, you find the multiplier. My multiplier is 0.499. Electrical wiring industrial, page 164, table 11-1. If you guys, the columns are the corrected power factor, and the rows are the original power factor. And you find the cross-section area, you cross-reference the two to find the multiplier. What they're doing, guys, is they did this table to make it easier for us to size. We can do the sizing in the long way. This is a much easier. And by the way, Brad, this table I believe is in this in this book too. This table is in this book. This is very common table, guys, is used. Go to the capacitor. I believe it's there. Okay, step number three. Step number three. K var equal M times KW. This is the rule that you guys are going to do. What was M? 0.499. What was KW that we calculated just a second ago? 664. 664 KW. And if you guys do the calculation here, you're going to end up with, came up with M equal 331. 331 K var. 331 K var. Any question, guys, about, here's the K var that I need to correct. This is the amount of capacitance that I need to add to increase the power factor to 97%. To increase the power factor to 97%.
You got 664.
664, Mr. Bab, is the KW that we just found it. Right here. Step one, that's from step number one.
Oh, I see. Okay, thank you.
Okay, guys, step number one, find the KW. Step number two, find the M, the multiplier. Step number three, multiply the multiplier by the KW, and that's how you find the size of your capacitor. Except, Brad, you're not going to go buy this 331. They don't make them. So what are you going to do? You're going to find the standard. Where would you find the standards? Just for Chad, from the manufacturers. Just for the test and just to be standardized, guys. What we're going to do, we're going to go to multiples of hundreds from now on. So I'm going to take, is that all we did? 4.44. So I'm going to take the 331 K var. This will be step number 4. Step number 4, take it to manufacturer standards. For me, just for the test, guys, multiples of 100. So what's the next standard multiple of 100, DJ? We have 331. What's the next 100? 400. Okay. 400 K var. Please do this one at least for the test. Otherwise, you're going to go basically find the manufacturers of a capacitor and find the next standard. Everybody's following with me, guys? You take what you got and go to, in my book, in Chad's book, just go to the next 100. 100, 200, 300, 400. Just for the sake of calculation. Real life, you're going to go to a manufacturer of a transformer and find the next standard. The next standard. 400 K var. 400 K var. So my capacitor, I know what size my capacitor is be. It's going to be a 400 K var. Now, the next is piece of cake. kVAR. For the test, guys, you will be either have this. Did you find it on? Okay, I'll swear it's there. Either I'll show you where in ugly this is located, this table, or you can open it at this book. I'll have to get back to it. Okay, any question, guys, about this? Can I go to number 2? All right, so number two is cab feeder. The feeder that's going to feed the cab, guys, right? You need to tie that cab. So here's what can I, the capacitor, equal 400 K divided by 1.73 times 480. You need to find, when we size conductor, guys, we size it based on current. So what's the current for this baby? And if you do the math, this will get you a 482 amps. Here's how much current this capacitor, I don't like the word consume, but how much current is this capacitor going to be contributing in kVAR to the system, So I need the conductors to be able to handle this. Okay, so that's step number 1 here. Step number 2, my friends, and then you take 1.35. I'll tell you where the 1.35 times 480, and that will get you 651 amp. 651 amps. This number, I use it. This number, guys, if anybody's wondering, is coming from 460.88. 460.88. If you guys go there, the capacitor, the code talk about the capacitors. It talks about the conductors have to be sized based on 1.35 times the full load current of the capacitor. Okay, 1.35 times 480. 2. Okay, so here's 651 amps. 651 amps. So that's, everybody knows where that 1.35 came from. The last thing is, I need to size the conductor. So you take the 65 I like to parallel. It's a big boy here. Divide by 2 to parallel them. If you guys divide by 2, you end up with 326 amps. Take this one to 310.16 under 75-degree column. And here's what you get. You're going to get, my friends, 2 sets of 3 conductors. Each one of them is 400 kCnm. Done. You're going to 2 sets of conductors. Each one of them is 2 sets of feeders. Each one of them is 3 conductors. Why 3? 3 phase. Do I need a neutral? No. Do I need a neutral? No. And believe it or not, Spencer, your capacitors will look something like this. I'm going to draw a capacitor without a contactor here. The heck is a capacitor? Here, is that here what we calculated here? It's going to look something like this. And each phase is going to be coming from here. Phase A, phase B, phase C, and this is all in a bank. All in a bank. That's how it's going to look like. Capacitors in a bank. Bring the 3 phases to them. Tied from one end, the phases. And this could be multiple of them, guys. It's just showing a symbol. Here's your phase A, phase B, and phase C. And we have 2 feeders. We know how to parallel. We parallel. Any question, guys, about up to this point? By the way, up to number 2, you guys have done that multiple times with me, except the multiplier 1.35. Can I go to the second one? So we need to find next, number 3. Number 3 is, guys, the overcurrent protection device. Cab overcurrent protection device. Here's what I would do, guys. And I'm going to tell you a disclaimer, 35 times, I do the same thing. 482 equals 651 amp. And You take the 651 amp. So this is step 1. Step 2 to 240.6 and go down to 600 amp. Go down, not up. And if you guys go read it, this is my interpretation. That's coming from 460.8b and CSK. It's not clear, Brad, how to do it. If you go there, it will tell you the overcome protection device have to be as low as practical. Oh, great. How low? I need a number to stick with it when I'm sizing. My rule is, guys, to use the same multiplier for the cable. I use it and I go down, because if you read through, it says as low as practical. Well, how are we going to do it? Unless you talk to the manufacturers. If the manufacturers tell you otherwise, you just do it. For the sake of sizing, guys, that's how I do it. Use the same multiplier, 1.35 times the same current, and go down. Any question, guys, about the overcome protection device? So it's a 600 amp fuse. 600 amp fuse. Is it wrong to put 400 amp fuse? No. Max 600 amp fuse. If the manufacturers, guys, say put 400 amp fuse, would you put the 600 amp fuse? No. If you don't know, this is how I want you, for the sake of argument, to calculate it. Number 4. Any question, guys? Every time I put CSK, this is opinion. Everybody knows that CSK is opinion, which means could be different people could do it differently. Last one, number 4. As you guys think, number 4 is cab disconnect. The cab disconnect, guys, the same thing. 1.35 times 482. That will give me a healthy 651 amp. That's the same rule. And then I take the 651, take it to DeWalt. What's the disconnect size? Is 3-12, right? 3-12, and that will get me. And go up. It's not standard for disconnect. Go up to 800 amp disconnect. And if you guys don't believe me, this baby here is coming from 460.8C.
8C, no?
8C, the disconnect.
Where does it say size in this?
That's the overcome protection device was B. The conductor was A, B, C. If you guys look at the article. So that's it. So we size, guys, the conductor, the overcome protection device, the disconnect, and the size of that cap. Now, Spencer, any system, you do it the same way. For any system, you do it the same way. Just a reminder, guys, Article 460 talk about capacitors. For you as designers, that's the most important things in the article. That's the most important as a designer. How to size the conductor, the disconnect, the overcome protection device for a capacitor. Where to put them, we'll talk about, guys, global and local, or main and local, how to put them, the advantage, disadvantages. Most of the time you're dealing with capacitors. If you have a manufacturing plant, you will be installing what do you call them, condensers or synchronous machines, and we size them the same way. KVAR wise, we size them the same way. The only thing is you need a sheet. I don't have it. That takes, guys, to get KVAR of 50, you need a 35 horsepower motor. So, but as far as you're concerned, when you go buy a 400 kVAR capacitor, you talk to you need a 400 kVAR capacitor, 483 phase, and they give you this big box. If you're buying a motor, a synchronous motor, you tell them that you need a 400 kVAR synchronous motor, and they'll give you this big motor, synchronous motor. And then you install it the same way, guys. You need a disconnect, an overcome protection device, a conductor, to tie it to your system. I had a fuse, but it could be also a circuit breaker, guys. If you have a circuit breaker, then you don't need a disconnect because your circuit breaker acts as your disconnect too. Any question, guys? Any question about that? I'm not going to start the second one. So that's basically similar for any system. Tomorrow we're not going to be here, but when we come, guys, I have one more thing. How do you, this is for the whole system. How do you size it for a motor? How do you size it for a motor? If you guys have chance, look at these tables. I'm going to be using these tables, guys, 165. It will tell you the size of the capacitors for U-frame and T-frame. U-frame and T-frame. So for example, very easy, guys, very easy. Let's tell you, by the way, U-frame, if you guys look at U-frame is the old motors. So in the test, I'm going to tell you if it's a U-frame, old, if it's T-frame and new labels. And by the way, Brad, these are in your book, the U-frame and T-frame about motors. If you guys come over here, let's just say we have a 350 horsepower motor. Can you guys look at this one? 300 in the bottom, 350 horsepower motor, and it's the most common RPM is 1800 RPM. At 1800 RPM, the kVAR that I need is 75. Can you guys see that? That's it. You don't need to do calculation, nothing. From this table, all what you have to do is the horsepower. Here's the horsepower, and here's the RPM, and I found 75. The table, this table is, guys, is these two tables are for 480 system. If you're using 208, way at the bottom, it says for maximum benefit, locate at the motor for a 208 system, use 33 larger. They're saying right at the bottom, guys, these two tables are for 480 system. If you are to size it for 208, which is not common on major motors, you really want them to be 480. If you are to use 208, all what you have to do is see that these numbers that you have here, multiply them by extra 33, so 1.33, up them by 1.33. We'll take an example about this one, guys. Again, U frame is the old, T frame is the new, and it will give you the size directly, no calculation needed. No calculation needed. So that's that one. I have another one, guys, another table I want you to look, and then I will do the example. But if you look at table 167, please, it will give you a typical size kVARs, and the size of the conductor, the fuse, and the switch already calculated for you at different voltages. So, for example, if you guys look, please, if you look at, let's look at the 20 kVAR. Can you guys see where it says 20 kVAR? 20. The full load amp of the 20 kVAR, the size of the wire, size wire at 240 is number 4. The fuse is 80. The switch is 100. At 480, the size is 8. The fuse is 40. The disconnect is 60. And at 600, they give you the size. So they did all the math for us, guys. They did the math for us. What I've done with you for motors, they already did the math. So this table, really nice. You can use it as a standard table. If you have, for example, if I have a capacitor, but it doesn't go higher than 125. Can you guys see that? It doesn't go higher than 125. So if you have a 125, guys, kVAR, the full load amp is 150. Do you know how they came up with 150? They take the 125 divided by 1.73 and 480, like I did. The size of the conductor 3 aught, and the overcome protection device is 250, and the disconnect is 400. So for the test, when I give you guys a test, if the sizes are within these ranges, please feel free to use the table. If the sizes of the kVARs are within these ranges, use this table, no problem. But you're going to see when I give you guys, I gave you a size of 400. How would you do it for 400? Here, it's not there. So you have to do the calculation that we did. For 400 kVAR, it's not there. It doesn't go that high. Manufacturers of capacitors, guys, have tables like these that give you the size and all this good stuff. If you find one of these from there, feel free to use it. Otherwise, the calculation that I gave you is very close. Okay, the only thing I owe you guys in this chapter is one more calculation for motors. One more calculation for motors. Thank you. Go eat.